Hello everyone, welcome to this tutorial on Quick, one of the most exciting and modern transport layer protocol we use in today's internet era. My name is Parth, and in this tutorial we are going to go deep into Quick, what it is, why it was created, how it works under the hood, and how we can actually observe it in the Wireshark. First, we will look at what is Quick. Quick stands for Quick UDP Internet Connections. It is a general-purpose connection-oriented transport layer protocol that was originally developed by Google in 2012. Later standardized by the IETF, the Internet Engineering Task Force, in May of 2021 as RFC 9000. Its core design provides us a low latency connection establishment, flow controlled streams, reliable delivery, congestion control support, and network path migration. In simpler terms, we can say Quick tries to In simpler terms, we can say Quick tries to provide many of the benefits that applications wanted from TCP plus TLC combined, but in a more modern and efficient design. Quick replaces both TCP and TLC layers in the stack protocol, as we can see here, it is given in the flow chart. Before Quick was introduced, every web connection used TCP plus a separate TLS handshake. Now let's look at why Quick was needed. To understand why Quick was needed, we really need to first look at its predecessor and their limitations, specifically TCP combined with TLS. First problem was head of the line blocking issue. TCP treats a connection as a single order stream of bytes. If one of the packet is lost anywhere in that stream, TCP stops and wait until the missing packet is retransmitted or received. This is called the head of line or HOL blocking. HTTP2 tried to solve the application level of HOL blocking by multiplexing multiple streams. But because all those streams are still shared on one TCP connection, a single packet loss freezes all the streams simultaneously. The Quick provides a simple solution by multiplexing independent streams. Loss on one stream will not affect the other streams. The second problem was with traditional HTTPS over TCP, client first needs a TCP handshake, then a TLS handshake before useful application data to fully flow, which adds up a significant delay. The Quick merges the transport and crypto into one RTT, resuming the sessions with zero RTT. Where in TLS 1.3 we still needed the two RTTs, which will create a significant latency delay. It is not happening with the Quick solution. Discussing the handshake comparison thoroughly, here we can see the on the left hand side there is the TCP plus TLS 1.3 handshake, and on the right hand side there is Quick handshake. Where we can Here we can see there are two handshakes happening before the actual data transfer happening in the TCP model, whereas in the Quick there is only one handshake taking place. This provides a lesser round trip time and a lesser latency as compared to the normal handshake that used to take place. Now let's move on to Quick's packet and frame structure. First, its packet type. There are two significant packet types in quick protocol: long headers and short headers. Long headers are used during the connection establishment phase. They are included with full source and destination connection IDs, the quick version number, and the packet field type. Four long header packets type are initial, 0 RTT, handshake, and retry, where initial carries the first crypto handshake message, client hello and server hello. The 0 RTT allows the client to send application data alongside the first flight of packets before the handshake completes. When a prior session exists, handshake carries the remainder of TLS 1.3 cryptographic handshakes. The retry used by the server is to validate the client's address before processing an initial packet, while the shorter header packets are used after the handshake completes. They are much more compact. They carry only the destination connection ID and the encrypted packet number. This keeps per packet overhead minimal and the bulk of the data transfer. Talking about streams and frames, there are different types of frame types and there are different purposes for them. Uh, as we can see here, The stream carries application data for specific stream, including stream ID, offset, and data. Acknowledgement acknowledges received packets, supports multi-range acknowledgements for better loss recovery. Crypto carries a TLS handshake data, not the application data. Connection close gracefully terminates the connection with an error code. New connection ID provides the peer with an alternative connection ID for migration in case the path challenge and path response used to validate network paths during the connection migration. Ping keeps the connection alive. Peer must respond with an acknowledgement in this case. Reset stream abruptly terminates a single stream without closing the connection. Here we can see a connection setup difference between header, long header and short header also. UDP carries a quick and quick carries the packet and packets carries the frame. So now let's look at the comparison between quick TCP plus TLS and UDP, the traditionally used protocols. Uh, HTTP is an application layer protocol. UDP is a simple transport layer protocol that does not provide us a built-in reliability. As we can see, there is a zero connection setup RTTs. Another major problem with TCP-based delivery is head-of-the-line blocking at the transport layer, where loss affecting one stream can delay other streams sharing the same connection, was the solution provided by Quick. In built-in inscriptions, there was no such inscription in UDP. It is mandatory in Quick, whereas and it is an add-on optional feature in TCP TLS. In connection migration, there is no connection migration options for TCP TLS and UDPs, where it is in Quick it is done with the help of connection ID. In multiplex streaming, there are limited amount of multiplex streaming options for TCP TLS, and in UDP it is completely an app dependent thing, which is whereas in Quick it is native and independent. In loss recovery, there are HOL risks in TCP and TLS, while Quick provides a fast per stream loss recovery system. In congestion control, there are congestion controls in TCP plus TLS and Quick, while there are no such thing in UDP. In OS level development, both TCP and UDP provided at kernel level, whereas at Quick it is provided at user space level. Moving on to real world application of Quick is in Google services. Google originally created the Quick. Gmail, Google Search, Google Drive, and YouTube has been using Quick since 2013 and 2014. It is estimated that Quick carries over 70% of Google's global traffic. In HTTP 3, Quick is a mandatory transport layer for HTTP 3. As of 2024, over 30% of websites globally supports the HTTP 3, including Cloudflare hosted sites, Facebook, and Shopify. In real-time media streaming, it is also useful. Application like Google Meet, YouTube Live benefits from Quick as it reduces its latency. In mobile applications, any Google's gRPs framework can transparently benefit from Quick. In Cloudflare's Edge network uses Quick to deliver content faster than the end user, faster to the end user, reducing the page load times, particularly on the mobile and congested networks. Quick is not just a theoretical protocol; it is a powering and a significant proportion of today's internet traffic. Security threats and mitigations of Quick are Quick is designed with strong security, but it still has security considerations. One of its issue is the zero RTT replay risk. RFC 9001 notes that the session resubmission, the reassumptions, and zero RTT requires the retained state, and reassumed connection can create a correlation and privacy concern if tickets are reused carelessly. Another issue is the denial of service and amplification risks, especially during the early connection setup before the client address is validated. Quick addresses this with an anti-amplification limit and address validation logic. A third issue is that it reduces the visibility of network monitoring because encryption hides most of the protocol from the passive observers. The that improves the privacy, but it can also complicate the traffic analysis with policy enforcements. Its mitigations can be using cautious application policies for zero RTT and avoid sending replay sensitive connections in early data, enforcing the address validation and anti-amplification protection during handshake processes, use of modern certificate validation and secure TLS configuration because Quick depends upon the TLS for authentication and key establishment. Use of endpoint-based logging and controlled observability tools rather than assuming middle boxes can inspect everything. Now let's discuss about the scalability of Quick. At connection level, because Quick runs at in user space, not in OS kernel, it can be updated and optimized without requiring OS patches. Teams can experiment with new congestion control algorithms. Quick ships with pluggable congestion control, supporting algorithms like Cubic, BBR, and Reno, and deploys them into without a system level change. Cloudflare, for instance, demonstrated serving millions of quick connections per server. Stream multiplexing at scale. Quick supports up to 2 to the power 62 simultaneous streams per connection. Each stream is independently flow controlled, meaning a slow stream or a lost packet on one stream does not slows down any other stream. This is the fundamental scalable than HTTP2 over TCP, where all streams are sharing a single window. Version negotiation. Quick has formal version negotiation mechanism built into its protocol. A server can signal to the client which version it supports, allowing the ecosystem to adapt on new protocol versions gradually. And while breaking the backward compatibility, this is a significant improvement over the TCP, which has taken the decades to evolve due to the middle box associations. Now let's look at the hands-on analysis on Wireshark. Um, I'm going to walk through the quick capture in Wireshark, and we are going to observe the handshake, that initial data exchange in real time. Um, as you can see here in the starting, uh, I have searched for quick in Wireshark. Um, Looking at the first of the few initial packages, we have used initial packet from client. This is equivalent to the client hello in TLS. Expanding the quick IETF here, we can look at the connection information. The long header flag is set to 1 here. This confirms the long header initial packet. The version, it shows the quick version 1 as per the RFC 9000. The destination connection ID, which is randomly generated value chosen by the client. This replaces the TCP4 tuple for identifying the connection. The crypto frame here, the crypto frame inside the carries the TLS client 1. Here you can see this carries the TLS 1.3 client hello, including the cipher suits and the key share data. The server responds with its own initial packet containing a crypto frame with the server hello, followed by the handshake packet containing server certificates and finished messages. Noting that all of this is happening in just one round trip. This is the Quick's 1 RT handshake. Here you can see the handshake is completing. Now comparing it with the TCP and TLS, TCP. Yes. Now let's open the TCP TLS handshake. Uh, Comparing the two timelines in the TCP TLS, we don't count the three round trips data before the data flow begins. In quick capture, the data begins after just one RTT. This is the performance advantages we are looking into the action. Here, the first there is the from the start. Let's see. First, there will be acknowledgement, then acknowledgement sequence, then sin. As it works on sin act basis, we can see.